In section 3b, we're going to talk about dichotomous tests and discrete probability distributions. So we'll start with the idea of a dichotomous test. Dichotomous test is basically, dichotomous means essentially that there's two possible outcomes. So it's important to talk about dichotomous tests and understand the basic ideas because while the error is a little more complicated in a statistical test is really a dichotomous test as well. So it's a good lead-in to what we'll do later on in the course when we talk about the idea of a statistical test. A statistical test might be something like, how effective is a drug at treating some illness? And when you do a statistical test, you have two outcomes, because either you're going to conclude that the drug was effective or you're not going to be able to conclude it was effective. So that's the idea of a dichotomous test, where you have those two outcomes. And dichotomous tests are really important because statistical tests are dichotomous. So here we look at some scenarios and we look at how good a dichotomous test is, or how good a test is, and we look at this test in terms of its error. So there's some terminology that comes along with this. We'll look at false positive and false negatives, and then of course we'll also look at the probability that we don't make an error, which is the idea of specificity and sensitivity. So here's the scenario that we'll use to talk through this. Suppose we are looking at how effective a rapid antigen test is at detecting if an individual has contracted COVID-19. The following table represents the outcomes for 263 individuals who took the test. So this is not actual data, I just made this up, but this is a useful tool in order to look at how good a test is. So the way we set up these tables is basically we let the rows of the table represent the outcomes of the test. So here we're using the rapid antigen test. So you can see the outcome of this test will either be positive or negative. If it's positive, that indicates that you have COVID. If it's negative, it indicates that you do not have COVID. Of course, these tests are not always right. They can make mistakes, and we can get a false positive or a false negative. The columns of the table then represent the actual condition. The person actually has COVID, or I just put no COVID for they do not have COVID. So the rows of the table represent, the columns of the table represent the actual condition. So from this information, we can figure out, well, what's the likelihood that this test gives the wrong conclusion? What's the probability of error? And the probability of error is going to be represented with two values, the false positive rate and the false negative rate. So the nice thing is all these values are nothing more than just conditional probabilities. So in a lot of ways, this is nothing different than what we did in the last section. These are just conditional probabilities, just a matter of reading the table based on these new terms. So you got to get comfortable with the terms, false positive rate, false negative rate, specificity, sensitivity. Okay, so let's start with the false positive rate. So false positive rate means the test says positive when it should not. That's what it tells you. So in this case, the test is going to say positive when the patient actually does not have COVID. So the condition here is that the patient does not have COVID. So always start with the condition first when you do conditional probabilities. So we're going to start with the person does not have COVID. So you look at how many people do not have COVID. That is 165. So that is your denominator of your probability. Then you say out of those 165, how many were positive? Or how many did the test say was positive? And that is, of course, 4. So the false positive rate, also written as just FPR, is just that 4 out of 165, which gives us a rate of 2.4%. So that's nothing more than a conditional probability. You just have to get used to the term and what it represents in terms of these tables. Going along with the false positive rate is the specificity. The way I like to remember that specificity goes with false positive is I just think about positive starts with a P, specificity has a P in it, it goes with the false positive. That's a good way to keep those straight. The false negative goes with sensitivity. Sensitivity has an N in it, so it goes with the negative. That's a good way to keep those straight. So the specificity is the probability basically that the test gets it right. So it is just the complement of the false positive rate. The false positive rate is the probability that the test gets it wrong. The specificity is the probability the test gets it right. So these both have the same condition. So both of these have the same condition of the person actually does not have COVID. So that means the denominator here is also 165. But now we're looking at those who are actually negative. They should be negative, and they are. So this is going to be 161 over 165. Of course, you can also just use the complement rule. You can just take 1 minus 4 over 165, and you'll get 161 over 165. That'll give you this specificity of 97.6%. And of course, these two things always have to add to be equal to 1 because they are complements. These are nothing more than conditional probabilities, so you just got to get used to the terms. And once you get used to the terms, if you understand conditional probability, these are not that bad. The false negative rate. The false negative rate, of course, means that the test says negative when it should not. The person was actually positive, so in this case, that means the person actually has COVID. So again, always start with the condition. So the condition here is that the individual has COVID. So that means your denominator here is going to be 98. And then out of those 98, 56 came back negative. So that means the probability of a false negative or a false negative rate here is going to be 56 over 98, which is 57.1%. So this is not actual data, but that would be, of course, a really high false negative rate. You wouldn't want your test to say negative 57% of the time whenever you did this test, because what would happen is you wouldn't be catching a lot of these COVID cases. So this is probably not a very good test. If this was actual data, we would say it's not a very good test because that is a really high false negative rate. Going along with that false negative rate is the sensitivity. So this works the same way as specificity goes with the false positive. Sensitivity goes with the false negative. It's nothing more than the complement. So the false negative is the probability of error. The sensitivity is the probability that it gets it right. So these again have the same condition. They both are conditioned on the person actually has COVID. The person has COVID. There are 98 people that have COVID. 42 times the test got it right and said the person did have COVID. So the probability of this is going to be 42 over 98. You can always just use the complement rule as well. 1 minus 56 over 98 will give you that 42 over 98, which is 42.9%. So overall, the false positive rate looked pretty reasonable, but the false negative rate in this test was really high, which means it's probably not a good test. There's probably a lot of error here. So that's all there is to a dichotomous test. It's really just a matter of being able to read the table and knowing what these terms are. Mathematically, it's nothing new because it's all just the same as that idea of conditional probability. It's just a matter of learning these terms. And like I said, these are important as we move into the idea of a statistical test, because a statistical test has basically the same idea of a false positive and false negative rate, because a statistical test can also be wrong. Okay, so let's move on to what we'll talk a little more about today, is the idea of a discrete probability distribution, because this is really kind of a new idea. The probability part is the same, but putting this together into a probability distribution is important. So a probability distribution really is just, we identify the outcomes X and the corresponding probabilities for each of those outcomes. So that's what a probability distribution is. We have this random variable X, we're going to list out the X values, and then we're going to find the probability for all those X values. That's what a probability distribution looks like. So here's our example. And sometimes I'll just give you the probability distribution, and sometimes I'll give you something like this where you can actually create the probability distribution. So the discrete random variable of interest X is the number of times a 6 is rolled when rolling a die 3 times. So we're going to roll a die 3 times and look at how many times I get a 6. So before we actually get to the random variable X, we really just need to go through kind of the process of rolling a die 3 times and look at the outcomes. So here's where you do have to be a little bit careful, because the way you define your outcomes is really important here. Because what you don't want to do is you don't want to say, well, whenever I roll the die the first time, there's 6 possible outcomes. And then when I roll it the second time, there's 6 more outcomes. And I roll it the third time, there's 6 more outcomes. Because that would be 6 times 6 times 6, or 216 possible outcomes. And technically, when you roll a die 3 times, there are 216 possible outcomes. But that's really not what we're concerned about here. So when you get a problem like this, you don't want to deal with all 216 outcomes, because really all we're interested in is the number of times I get a 6. So each time I roll the die, really all I care about is either I get a 6 or I do not get a 6. So that's really all that matters. It doesn't matter what the actual number is other than I get a 6 or I don't get a 6. And it's really beneficial to think about it like this, because if you do, then you have basically 2 possible outcomes each time you roll the die, which is 2 times 2 times 2, or 8 possible outcomes in this experiment. So when you think about it like that, you reduce the number of outcomes you have to deal with. Instead of dealing with 216 outcomes, I now only have to deal with 8 possible outcomes. So that's the way to think about this problem. So what we're going to start with is we're going to start with the idea of a tree diagram. We're going to create a tree diagram for the possible outcomes. We're going to let 6 be that we roll a 6, and we're going to let n represent that we don't roll a 6. And you could identify these however you want, but these are the 2 outcomes I'm interested in. Either I roll a 6 or I don't. So to create the tree diagram, you just draw it like this. This is your tree diagram. So you can see on each outcome, either you get a 6 or you do not get a 6. And based on this tree diagram, you can see the first outcome there is I get a 6 on each roll. So that is that I get 3 6s. The second outcome is I get a 6, and then not a 6, and so on. So you can just follow the branch of the tree diagram. That's nothing new. We've talked about the tree diagram in the last section. When you have a series of operations like this, a tree diagram is a good tool. If we just list out these outcomes, this is a list of the outcomes. Because that's really the goal of this, is just to get a list of our outcomes so we can start to understand the probability of these outcomes whenever we roll a die 3 times and we're interested in how many 6s we get. So the next step is to think about probability. So let's calculate the probability for each of these outcomes in the tree diagram. So I'm just going to give you a list of these same outcomes. So it's these same outcomes we have listed there. And then we'll talk about the probability. So here is where you have to be a little careful when you think about how to calculate the probability for each of these outcomes, because there are 8 possible outcomes here. But the thing that you cannot do, and the thing you got to be careful of, is the probability of each of these outcomes is not just 1 out of 8, because that's the common mistake that people will make. They'll say, well, there's 8 outcomes, each one is equally likely, the probability is 1 out of 8. But the problem here is the outcomes are not equally likely. And the reason why they are not equally likely is because the probability of getting a 6 is 1 out of 6. The probability of not getting a 6 is 5 out of 6. So obviously those 2 things are not equal. You're way more likely to not get a 6 than you are to get a 6, because you only get a 6 1 out of every 6 times. So because of that, these probabilities are not the same. So what you have to do, and a safe thing to always do when you have a tree diagram and you're looking at probability, is to use the idea of the multiplication rule. Because the multiplication rule says when you do a series of things, if you find the probability of each one and multiply them together, it gives you the probability that they all occur. And that's the way to do these problems, is to do these problems using the multiplication rule. So for example, the probability of getting 3 6s, well, the probability I get a 6 on the first roll is 1 out of 6. The probability I get a 6 on the second roll is 1 out of 6, and the probability I get a 6 on the third roll is 1 out of 6. So if I take 1 6 times 1 6 times 1 6, that'll give me the probability that I get all 3 6s. And you can see I have that written out there. That will give you 1 over 216. That's the probability that you get all 3 6s. The probability that I get a 6 and then another 6 and then not a 6, you can see that probability by the multiplication rule is 1 6 times 1 6 times 5 6, which will give us 5 over 216. And all these work the same way. The next one, the probability of 6, not a 6, 6, is 1 6 times 5 6 times 1 6. That's 5 over 216. The probability of getting a 6 and then not a 6 and not a 6 is 1 over 6 times 5 over 6 times 5 over 6, which gives you 25 over 216. And all these work the same way. We just use that multiplication rule. And this will give us the probabilities for each of the outcomes from this tree diagram. And of course, these are not equal, so you have to use the multiplication rule here. Now, technically, if the probability for each of the outcomes was equally likely, then these probabilities would just be 1 out of 8. But a safe thing to do if you're ever not sure is just to use this idea of the multiplication rule. So this is kind of the first step in creating the probability distribution. So that is the next step, is so we've calculated the probability for the outcomes. Now let's create the probability distribution for X. So x is the number of 6s that I get when I roll a die 3 times. So that means the possible outcomes for x are going to be 0, 1, 2, or 3, because whenever I roll a die 3 times, I'm either going to get a 6 0 times, 1 time, 2 times, or 3 times. Those are the only possibilities. So your probability distribution is going to look like this, and I'll talk you through it. But first, you can see we list out the x's. The x's are either 0, 1, 2, or 3. Those are the possible outcomes for how many times I'm going to get a 6 when I roll a die 3 times. And then the whole point of creating this tree diagram and coming up with these probabilities is now we can use this information to figure out the probability for each of these x outcomes. So the probability of getting 0 6s, well, if you look to the left there, you can see 0 6s means you get n, and n. So that probability is 125 over 6, so that one's simple. There's only one way to not get any 6s. It means you don't get any on any of the die, so that's just 125 over 216. The probability of getting 1 6. Well, there's actually a few different ways that this can happen. So if you look down through the list, there's actually 3 of these outcomes from the tree diagram that have exactly 1 6, because it could be that the first outcome is a 6 and the other 2 are not. It could be that the middle outcome is a 6 and the other 2 are not. Or it could be that the last outcome is a 6 and the other 2 are not. So there's 3 different ways for this to happen. And if you look through these outcomes, you'll see that all 3 ways have a probability of 25 over 216. So we basically need to add those together or just multiply it by 3. So we get 75 over 216 for the probability of getting exactly 1 6. If we look at getting 2 6s, there are actually also 3 ways that can happen, because getting 2 6s means one of the outcomes is not a 6. So it could be the first one that's not a 6, the second one that's not a 6, or the third one that's not a 6. So there's 3 ways for this to happen. Again, if you look at through all those outcomes where there's exactly 2 6s, you'll see that the probability for all of those is 5 over 216. So if you take 3 times that, you get 15 over 216. And that is the probability that you get exactly 2 6s. The probability that you get exactly 3 6s, that is only that first outcome where we get 3 6s, which is 1 over 216. And that's what a probability distribution is. A probability distribution identifies 2 things. It identifies the outcomes x, and then it identifies the corresponding probability. So we usually just create columns like this, and we create one column that is the x values and another column that is the probability of x values. And we would typically just write it in the simpler form where we don't have the math included in the table. We just have a list of the x's, and then we have a list of the probability of x's. So when you do this and you go through this process and you create a probability distribution, one of the things that it's good to do is just to make sure that it's valid, make sure that you didn't make any mistakes. And this is not a guarantee, but there's a few things that you should check in order to make sure that it is a valid discrete probability distribution. So the first thing you check is obvious. You just want to make sure that the random variable x is discrete, and that's going to really be done for you. But you should know that in order for something to be a valid discrete probability distribution, of course the random variable x has to be discrete. And by discrete, we mean it's got to be countable. It's got to be something that you can list. Remember, we talked about this earlier in the class, the difference between discrete and continuous. Discrete is something that you count. It has specific outcomes that you can list. Continuous is something that you measure, which means its continuous variables has an infinite number of outcomes, because between any 2 distinct outcomes on the real number line, there's an infinite number of other outcomes. So in a discrete case, it's nice because we just list out x, and then we identify the probability for each of those x's. The next one is something you should always check when you do a probability. You should always make sure that the probability is within the possible range for probability, which all probability values has to be between 0 and 1. And of course, that is the case here. All of these probabilities are between 0 and 1, and that will always be the case. Anytime you calculate a probability, you can never have a negative probability, and you can never have a probability greater than 1, because 0 means something never happens, 1 means it always happens. You can't be beyond either of those endpoints. The third one is an important one, because this is a good thing to check when you go to create a probability distribution, because if this is not true, then you know you made a mistake. So it's always good to go back and just sum the probabilities, because in order for it to be a valid probability distribution, the total probability has to be 1 or 100% because it makes up 100% of the possible outcomes. So that only makes sense, right? The total probability or the total probability in the sample space has to equal the total possible probability, which is 1 or 100%. So notice in this table, if we go up and we add these, we get 125 over 216. So 125 plus 75 is 200, plus 15 is 215, plus 1 is 216. So we end up with 216 over 216 here. So that gives us the total probability of 1. So we can be confident that these numbers are probably correct. They meet this criteria of being a valid probability distribution. It's a good check because lots of times if you make a mistake, the numbers won't add to be equal to 1, and then you'll know, at least you might not know where the mistake is, but at least you'll know there is a mistake in the work somewhere. Okay, so once we calculate a probability, and probability distributions are so important in statistics because whenever we go to control error in inferential statistics, we use this idea of probability distribution to control error, which is why we spend time on probability distributions. You got to know the basics of probability, and then you have to know what a probability distribution is and how we use it, because that's how we control error in inferential statistics. Because our underlying, whenever we take a random sample, this underlying distribution is going to be the way that we calculate and control the probability of error when we get to that point. I don't want to say too much about that now. The next thing that we want to do anytime we have a random variable is we want to be able to describe that random variable. So we have this random variable x, right? This random variable x is something that we can describe. So the most common way to describe a random variable is with its mean and its standard deviation. So let's calculate the mean and standard deviation in this case. Now, a couple things change when you do this. The first thing that changes is this is different than what we did before, because before we took a sample and we calculated a sample mean. Here, we're not taking a sample. These x values actually represent all the possible x values. So that means we have the population information here. So this is going to be a population mean instead of a sample mean. So that's the first difference. The second difference is when we took a simple random sample and we calculated the mean from a sample, we knew that all the probabilities were equal. In a probability distribution, most of the time all the probabilities are not equal. So you cannot use the typical formula of just adding up your x's and dividing by how many you have. That formula only works if all the probabilities are the same, which we know to be true when we take a simple random sample. But we also know in this example that the probabilities are not all the same. So the only way that you'll be able to add up your x's and divide by how many you have is if all the probabilities are the same. So don't expect that to happen in a probability distribution. You need to use this other formula, which gives you basically a weighted average. Because you can see you're way more likely to get 0 6s in this example than you are to get 3 6s. So that means that value of 0 needs to be weighted more in your mean than the value of 3, because it's going to happen way more often. Whenever we talk about the mean in a probability distribution, you will sometimes also hear it called the expected value. So if you hear the term expected value is nothing more than the mean of a probability distribution. They say, what's the expected outcome or the expected value? That is the average value or the mean of the probability distribution. Okay, so to calculate the mean, let's go through the steps here. To calculate the mean is basically the sum of x times p of x. So this is not a difficult thing to do. The mean is pretty straightforward. Once you have your probability distribution set up, and either you will create it yourself or you'll be given the probability distribution, then what you do is you just create another column to the right of that. That column will just be x times p of x. And to get that column, all you have to do is multiply across. You just take your x values and multiply it by its corresponding probabilities. So you can see here, if you take 0 times 125 over 216, you get 0. If you take 1 times 75 over 216, you get 75 over 216. If you take 2 times 15 over 216, you get 30 over 216. And if you take 3 times 1 over 216, you get 3 over 216. So all you're doing is multiplying across there, and that gives you that list of x times p of x values. If you sum that list, it'll give you the mean. The mean is the sum of x times p of x, and you can see at the bottom, if you take 75 plus 30 plus 3, you get 108 over 216. That will be the mean, which is nothing more than 0.5. The other thing to notice here is notice the notation for the mean. The mean, you see that symbol there? That's actually a Greek letter. It's a lowercase mu. That is the symbol that we use for the population mean. So it is important that you remember that for the sample mean, we use x bar. For the population mean, we use this new symbol, which is a lowercase mu. So the population mean mu, in this case, equals 0.5. That's the way you calculate the mean. That's always the process you go through when you calculate the mean of a discrete probability distribution. If you think about this mean actually makes some sense if you think about it. Just think, if you roll a die 6 times, you're most likely to get a 6 how many times? Well, on average, you should get a 6 1 out of every 6 times, right? So if you roll a die 6 times, the average should be 1, because you should get on average 1 out of 6. So that means if you roll it 3 times, you should get half of that. So you should get half of 1, which is 0.5, and that's what you get here. That is the mean. So it's not like you have to see that, but that is a way to see that the mean does make sense in this case. The mean is 0.5. So the other thing that we use in order to describe a distribution is a standard deviation. The most common way to describe a distribution, as we've talked about, is with the mean and with the standard deviation. So the standard deviation is a little more messy here. The standard deviation is technically the sum of x squared times p of x minus the mean squared. So you need a couple more columns here in order to get to the standard deviation. So you always basically use these same columns. What I recommend you do is just create that 4th column there, which is x squared. So to do that, you just look at your x values and you square them. So you get 0 squared, 1 squared, 2 squared, and 3 squared. That's where you get those x squared values. And then the last column is the one that we really need, which is x squared times p of x. So make sure you multiply the correct columns here. You're multiplying the x squared column times the p of x column. So you're taking 0 times 125 over 216, which is 0. You're taking 1 times 75 over 216, which is 75 over 216. You're taking 4 times 15 over 216. So make sure you get that right column. Make sure you get the p of x. You can see the probability for 2 is 15 over 216. So you multiply that by 4, you get 60 over 216. And then we get 1 over 216 times 9. That's 9 over 216. So that gives us the x squared times p of x values. So the first step in calculating standard deviation is, well, we have to get variance first. So you have to get this sum of x squared times p of x. That's how you start to get the variance, is through this sum of x squared times p of x. That is always your first step. Here's the variance formula. The variance is actually denoted by this sigma squared. So this is actually a lowercase sigma. The capital sum symbol is a capital sigma in the Greek alphabet. We actually use a lowercase sigma squared for the variance, and then of course just a lowercase sigma for the standard deviation. Typically, whenever we use Greek letters, typically that means we're dealing with parameters. So these are values from the population, right? We said this was the population mean, population standard deviation. Typically, when we deal with population values, we use Greek symbols to represent those values, and that's why you see these Greek letters. Most of the time with sample values, you'll see our alphabet. So you'll see like X bar represents the sample mean. We use a letter from our alphabet, which is X with a bar over top of it, to represent the sample mean. And then we use mu, the Greek letter, to represent the population mean. Same thing with standard deviation. Sample standard deviation is S. Population standard deviation is sigma. So the sigma squared represents the population standard deviation. The way you calculate that is you take the sum of x squared times p of x, subtract the mean squared. So we just calculated the sum of x squared times p of x. That's what that 144 over 216 is. That's the whole point of getting that. Once you get that, it's simple to get variance. You just subtract the mean squared. We just said that the mean was 0.5, so you just subtract 0.5 squared, and that will give you the variance. The variance in this case is 0.417. So remember, if you're asked for standard deviation, the first step is always to get the variance, because the standard deviation is the square root of the variance. So once we get that variance, you can see we use the sigma symbol for standard deviation. We take the square root of that variance. That's the way standard deviation always works. That gives us the standard deviation, which is 0.645. So the mean in this case is 0.5. The standard deviation is 0.645. So probably not something you're too interested in. When you roll a die 3 times, the number of 6s you get has a mean of 0.5 and a standard deviation of 0.645. Probably not that useful of an example, but it's a very important example in terms of the process of how these work. I will tell you that lots of times the mean or the expected value is a very useful value in these probability distributions. Lots of times the standard deviation is not so useful other than statistically. So it is important that you're able to calculate standard deviation, but the standard deviation is really important more as we move forward in the class. The mean is lots of times an important value for these kinds of questions. So let me give you an example where the mean is actually a more useful value than something like just rolling the die 3 times. So let's think about the idea of roulette. So if you ever go to Vegas or go to a casino somewhere, one of the things that you can do is you can bet on the roulette wheel. So if you don't know anything about roulette, basically they put a ball in the wheel and they spin it, and it's equally likely to land on any of the spots. And there's different ways that you can make bets. But a roulette wheel has 38 slots. 18 of the slots are black, and you can see a picture of a typical roulette wheel here. 18 are red, and 2 are green. The wheel is spun, and a ball is equally likely to land in any of the slots. So if you bet $1 on red, then you will win $2 if the ball lands on a red slot. So that's basically the way this works. If you bet on either red or black, which are common bets, if the ball lands on either of those, if the ball lands on red and you bet on red, then you basically double your money. So if you bet $1, you win $2. If you bet $100, you would win $200. So we're just going to look at a $1 bet. But of course, this would extend to bigger bets. You would just be, instead of, basically you always just double your money if you win. Okay, so the first thing that we need to do in order to think about the scenario, because basically what we want to do is we want to figure out, well, if I do this and I bet $1, how much am I going to win on average? So the first step is always to set up your probability distribution. So the first thing we're going to do is we're going to give a probability distribution for our winnings here. So there are 2 possible outcomes for the winnings, because whenever you bet this $1, you're either going to win nothing. If the ball does not land on red, you win nothing. Or you're going to win $2 if the ball actually lands on red. So your probability distribution is going to look like this right here. There's only 2 possible outcomes for X. X just means I win $0 or I win $2. Then you have to think about the probability. Well, there are 18 red slots, as we just mentioned. So that means the probability that I win $2 is 18 over 38. The probability that I don't win, well, there are 18 black slots. There are also 2 green slots. And because of that, there are 20 possibilities that I don't win out of the 38. So the probability that I don't win, or the probability that I win 0, is 20 out of 38. So this is the probability distribution, the discrete probability distribution for this scenario. So now once we have the probability distribution, then we can start to think about the mean. And start to think about our winnings. So in order to calculate the mean, or the expected value, the expected winnings for a $1 bet, so I need to do the same thing as what I did in the last example. I need to create another column that is x times p of x. I create that other column that's x times p of x, and the way I do that is I just multiply across. I get 0 times 20 over 38. That gives me 0. 2 times 18 over 38 gives me 36 over 38. So that means if I sum that column, that's the sum of x times p of x, that gives me 36 over 38. So that is the mean. So you can see the mean here is 36 over 38, which if you round that to a couple decimal places, and we're dealing with money here, so I round to 2 decimal places, you get 0.95. So this is actually an important value here. So basically, for every dollar you bet, whenever you play roulette, for every dollar you bet, on average, you win 95 cents. So that's how it works. So basically, probability always works in the long run. That's why those casinos can build all those fancy buildings. That's where they get all that money from, is every time someone bets $1, they basically get 5 cents of it. So it doesn't mean no one can ever win. It just means in the long run, for every dollar someone bets, they're getting 5 cents of it. And that's the way it works. So of course, if someone bets $100, then on average they would win $95. That's always the way it works. You basically recoup 95% of your money in the long run. Probability works in the long run. Never forget that. It doesn't mean in the short run you couldn't win. But in the long run, if you play long enough, then the odds are not in your favor. And that's how all these games work. They all work so that the casino, of course, makes a lot of money. So there are a lot of ways to bet in roulette. So let me show you one other example with roulette. So we're going to look at what's called a column bet. So on the table, you can see a picture here. So you can lay chips out on the table in these different places to place a bet. So one of the things that you can do is you can bet what's called a column bet. So you can see that the numbers there, the red and blacks, are laid out in 3 columns. And basically, like the first column is the numbers 1, 4, 7, 10, 13, 16, 19, and so on. So you see that we have those numbers listed out in that column. So a column bet basically means if anything in your column is where the ball lands, then you win. Otherwise, you lose. So let me read the scenario. Gamblers bet on roulette by placing chips on a table that lays out the numbers and colors of the 38 slots in the roulette wheel. So the red and black slots are arranged on the table in 3 columns of 12 slots each. So there are 12 slots in each column. So the 0 and 00, the 2 green slots, those are not in any of the columns. And that's ultimately how they make their money, is they make their money because those 2 green slots means that they are more likely to win than you are. That's basically where that 5 cents comes from. The nice thing about a column bet, though, is a column bet, if you bet $1, then you actually win $3, so you win more. But they counteract that, of course, with the probability of winning, because there are 18 red slots, so if you bet on red, you have a probability of winning of 18 over 38. But there's only 12 possible winning slots when you bet on a column, so you're reducing your likelihood of winning when you bet on a column, but you're going to win more if you do win. And you'll see what happens here. So let's do the same thing as we did on the last one. Let's give the discrete probability distribution for the winnings of a $1 column bet. So we're either going to win $0 or $3. So that means my x values is just simply 0 or 3. We just said the probability that you win $3 is 12 over 38 because there are 12 outcomes that satisfy a given column. That means the probability that you don't win is you have the other 24 outcomes in the other 2 columns, along with the 2 green slots, which means the probability you don't win is 26 out of 38. Then we can calculate our mean by just creating that other column, or expected winnings. We calculate our mean by creating this other column. So we have, take x times p of x, we get 0 times 26 over 38 is 0. 3 times 12 over 38 is 36 over 38. We add 0 and 36 over 38. We get 36 over 38. That number should look familiar to you. That means the mean here is 95 cents. So notice it's exactly the same as what the mean was if you bet on red. It's just a question of, here you actually win more if you win, but you're less likely to win it. So those things just balance out. And at the end of the day, you win 95 cents for every dollar you bet. And there are a bunch of different ways you can bet in roulette, but you calculate any of them, and what you'll find is for every dollar you bet, on average, you win 95 cents. Some of them you'll win more if you do win, but to counteract that, the probability of winning is lower, and those things balance out, and basically you win 95 cents for every dollar. So this is a more applicable scenario where you can see a use for the actual mean. There's also examples in the notes, and the mean is lots of times actually a useful example. Standard deviation is important statistically, like I said earlier, but it's important that we're able to calculate it because it is very important statistically. So those are the big things in this section. You got to understand the terminology that goes along with the dichotomous test, understand what a dichotomous test is, that terminology, how to calculate those values, but that's really nothing new mathematically. It's just a matter of getting comfortable with that terminology. And then we need to understand this idea of a discrete probability distribution, what one is, how to lay one out. And then if you have one, you need to understand what to look for to make sure it's valid. And then you need to be able to calculate the mean and the standard deviation for a discrete probability distribution. This is really your introduction to probability distributions. Probability distributions is important. We're going to talk more about probability distributions in the next section. We'll move to the continuous case. So it's really important that you get a good grasp on this idea of a discrete probability distribution. This is actually the simpler of the two cases, but you need to understand what the distribution looks like, how to lay one out, how to calculate and summarize it with its mean and standard deviation. That's the focus of this section. So that is the end of section that is the end of this section. That is the end of section 3B.